In this video, we'll be studying practice questions 61 through 70 with their complete explanations. And this is from the state of California released CST questions. So, I've underlined here what we need to be watching for. And that's right up in this area. And what are we watching for? The circuit is interrupted by a solution. A solution is what we see right here. This guy is a battery. This, of course, is a light bulb. And then the wires are connected from this end of the light bulb to the other end of the light bulb, and from this end of the battery to the other end of the battery. And everything would work all the time if we didn't have this solution here in the middle. And that solution, if it has anything in the water, it's going to conduct electricity. Any ions in the water, I should say. So, what is going to form ions that would cause this light to go on? Sodium nitrate is sodium ions and nitrate ions. So those guys are going to be able to conduct electricity. Now, hydrochloric acid is hydrogen ions and chloride ions, another ionic compound. It's not ionic in the sense of a metal with a nonmetal, but it does form ions. In letter A here, we've got a metal with a nonmetal. This is just an acid. So any salt, and a salt is a metal with a nonmetal, any salt will automatically form ions. Now, this is a salt, but it's not a metal with a nonmetal. It's a nonmetal, a metal with a nonmetal. It's not a metal with a nonmetal. It is a nonmetal with a nonmetal, but this nonmetal here, this ammonium dude, is the ammonium ion, NH4, 1+. And the sulfate is the SO4, 2- ion. So these guys form ions like crazy. Sucrose? No, baby. That one does not form ions. I've set up an Elmo here so you can see a similar kind of a situation. Here's water. This is called deionized water. Has no metal or no ions in the water. This is also no metals or no ions, that is, in the water. And what do the ions do? They'll do just like this piece of metal does. They will connect the circuit, and the light goes on, as you can see. Now, let's go ahead and put the little conductor apparatus down into the water, and let's watch what happens as I pour in an acid. This happens to be sulfuric acid, but watch what happens. The light is not going to come on immediately because the ions have to move in the water. Ooh, that happened pretty fast. That is what we call a strong acid, and it ionizes 100%. So that guy came up right away. Now, let's get the other stuff. This is just plain old salt. Okay? Salt that you buy at the store. Okay? Plain salt. Let's go ahead and put the conductivity apparatus into here. And now this guy's going to start conducting, but it's going to start conducting very slowly. And looks like I didn't have a whole lot in there. You see the light is not that bright. It's coming up. As the ions slowly dissolve in the water, they're going to make that light get brighter and brighter. And if I had a better camera, you would be able to see that difference dramatically. But you did see it get from lighter to, hardly anything, to a fairly bright light. And as that continues, let's see if I can, okay, this guy, I can see it here with my eyes that that's getting really, really bright. More ions, more conductivity. In this question, they're asking you to look for an observable property of acids. In letter A, they become slippery. This is typical of a base. Bases become slippery. And they produce salts when they're mixed with other acids No, they produce salts when they are mixed with a base. They become more acidic when mixed with a base. That's crazy. Okay? They're not going to do that. An observable property of many acids, they'll become more acidic when mixed with base. No, why? Because an acid plus a base gives you salt and water, as we saw in the last guy. Okay, it's only letter D. Why is it letter D? Because an acid plus a metal will always produce hydrogen, is what they're saying here, and that is true. And I've given you an example right here of nitric acid reacting with aluminum to form the salt aluminum nitrate. That's this guy, and of course the hydrogen. In this question, where they're actually saying in the question what I just wrote up here before we started. And that is that the copper hydroxide, copper 2 hydroxide, is reacting with this acid. Remember, an acid plus a base give you water and a salt. When that happens, that means that the copper 2 hydroxide is being dissolved. So letter B describes that perfectly. It says we'll form water and soluble copper 2 nitrate. Copper 2 nitrate is what we have over here, which really has nothing to do with it, but what does happen is that the copper 2 hydroxide will be dissolved. Now, it'll dissolve most solids, letter C, including sodium nitrate. Sodium nitrate, this guy is not a solid. It shows you right up here that he's aqueous. So that's a bogey. Letter D reacts with the copper 2 nitrate. The copper 2 nitrate is over here, and why would it react with the copper 2 nitrate? It doesn't mean anything because copper 2 nitrate is aqueous already. So the nitric acid is not going to affect anything that way. And then up here in letter A, dilutes the solution, making the precipitate dissolve. It does make the precipitate dissolve, but diluting the solution is not why. Okay? That's why letter A doesn't work. In this question, potassium hydroxide, KOH, is a strong base because, as I wrote in blue up here, strong bases ionize 100%. It is also true of strong acids. Strong acids also ionize 100%. What does that mean? They form ions. Every little one of them is broken up and forms ions, which is exceptionally good at getting ions into the water. So let's look at letter A and see why. Well, first of all, C is correct. Easily releases. What does that mean? That means it ionizes 100%. It lets go, the two ions let go of each other very easily in water, so water can break them apart. Now, that's the correct answer. Why do the other answers not work? Reacts to form salt crystals in water. KOH doesn't do that. It has to react with an acid to do that. Does not, okay, that rules out letter A. Now let's look at B. Does not dissolve in water. It does. It dissolves very easily. And that's why it ionizes 100%, or the fact that it ionizes 100% is why it dissolves in water. And then in letter D, does not conduct an electric current. You just saw the light bulb test, and potassium hydroxide will light that light bulb up really, really well. So that's just a false statement. In this question, you have to understand the pH scale. 14 is your strongest or most concentrated hydroxide solution, which is the most concentrated base. Your smallest pH is the most acidic one will be your smallest pH, and that will have the highest concentration of hydrogen ions. So that's why your answer here is letter C. This is just a little bit of background now on acids and bases, so you can see what happens on the pH and pOH scale. pH at 0, you have your most acidic, or close to the most, because pHs can actually go down to a 1 minus, or minus 1. So, we're not all the way there at a 0. So, a pH of 0 means a pOH of 14. You see it here, it says pH, here it says pOH. So pH and pOH always add to 14. 3 plus 11, 14. 4 plus 10, 14. 14 plus 0. Okay? We get 14 all the time. So this little pH scale is very, very valuable because it also shows you the correspondence of the hydrogen ion concentration, which is in powers of 10. And you'll notice that a power of 10 to the minus 1 is a pH of 1 because pH is a negative log of this number. And 10 to any power, when we take a log of it, is going to be whatever the power is. Because pH is a negative log, the actual log of this 10 to the minus 1 is 1 minus. But because the log is a negative to give you a pH, you got to change that minus to a plus, and that's why this guy is a 1 plus. So a little lesson, or a little quick review there on acids and bases and what the pHs mean. In this particular question, you need to understand what this forward arrow means. Okay, I'm trying to write here. Let's see if we can get this going. So the forward arrow here is meaning as we go forward, for some reason it won't write, but we will say that forward arrow is going to be something that will show that the reaction is moving to the right. So letter C has to be the correct answer, and why is that? We have to know a little bit about Le Chatelier. An increase in the concentration of HCl. So HCl is up. Now what Le Chatelier wants to do is exactly the opposite. I know this isn't a Le Chatelier problem because it's not a back and forth arrow, but the same principles will apply. Le Chat in the black arrow is showing that we want to go down. And to go down, he has to move the reaction towards the opposite side, which means a left shift. So, which of these describes the rate of the chemical reaction? It's going to be the formation of the HCl. And the HCl will increase. Actually, Le Chat doesn't have a whole lot to do with this. But the forward reaction is what we're trying to monitor. And when we have reaction going forward, it will form more HCl. And if the problem did ask you anything about what happens as we add HCl, of course, that would be an up arrow, the blue arrow that you see over the HCl, and Le Chat would want to move it down, and so that would drive our reaction to the left by adding HCl. So that's the why and wherefore of that particular problem. In this question, we do have a Le Chat. Okay, which of the following changes will cause an increase in the rate of the reaction? As Le Chat drives to the right, so we want a right-hand shift going that direction. Okay, to get a right-hand shift, decreasing the temperature isn't going to do anything. This is a bogey, not good, because there is no exothermic or endothermic reaction. If it were exothermic, we'd have heat over here. If it were endothermic, we would have heat over here. We don't have either one. Decreasing the concentration of this dude. If I put this guy down, Le Chat is going to want to make more. To make more, he has to move to the same side, which in this case would make the reaction move backward, and that would slow down the reaction. So this winds up being a bogey as well. And in letter C, an increase in the concentration of HBr. Okay, so if I were to put in more HBr, Le Chatelier wants it to go down. To go down, he has to move to the opposite side, which again moves it in the wrong direction. That would be to the left. So the one that we want to go for is actually letter D, and that's increasing the concentration of bromine. Le Chat then wants to decrease the bromine, and to decrease the bromine, he has to move the reaction to the opposite side, which is a shift to the left, which is going to wind up speeding up the reaction. Okay, I'm going to hit all the wrong answers first. Let's start with letter A. This question is asking what I underlined in blue. We want to decrease the rate of the reaction. Which of these answers is going to do that? Well, the rate of reaction will be controlled by Le Chatelier principles. So let's remove the CO2. CO2 down. What does Le Chat want to do? Yes, Le Chat wants to increase it. To increase it, he has to go to the same side. That's going to move the forward reaction, which is not going to decrease the rate of the reaction. That will increase it. So this guy's a bogey. All right. Next thing, raising the temperature of the reaction. We have no idea what that's going to do because it's not exothermic or endothermic. There's no heat over on this side. There's no heat over on this side. So heat will have no effect, and this guy's a bogey. Now, let's go down to letter D because C's our the correct answer. And we're going to add carbon monoxide. So carbon monoxide up. What does Le Chat want to do? He wants to put it down. And so if he's going to put it down, we've got to use it up, which is to shift to the opposite side. And that will increase the rate of reaction because that will make more CO2. And that's not what we want to do. So now we can look at this guy and see why C is the correct answer. Increasing the volume inside the reaction chamber. Okay, if the volume goes up, if volume is up, Le Chat wants to make it go down. Now, how does he make the volume go down? He has to go to the side with fewer moles. And if we count up the moles, we see 2 plus 1. No, you don't see a 1 there, but it's always assumed if there's no coefficient. So we've got 2 plus 1 on the left and 2 on the right. So what's going to make it go down? Okay, we want to decrease the volume. We've got to go to the right-hand side. And if we're going to decrease the volume, that will cause the reaction to want to make more volume, and to make more volume, we've got to go to the side with fewer moles. Le Chatelier has a problem, though. He cannot mess with volume. But what happens when the volume does go up? We lower the pressure. So if the pressure goes down, how is Le Chat going to make more pressure? He'll make more pressure by going to the left side, which is going to have more moles, and that will increase the pressure and partially offset that increase in volume. And as it does that, shifting to the left is going to cause a decrease in the reaction rate, which this reaction is going to the right. And that's how you go through the logic of this problem. Okay, in this question, we just want to know what a catalyst does. And what a catalyst does is it lowers the activation energy, and that's all that it does. As it lowers the activation energy, it will speed up the reaction. Increasing the equilibrium constant in favor of products is going the wrong way. Raising the temperature at which the reaction occurs is, in this particular case, unknown because we don't know whether it's an exothermic or endothermic reaction. And increasing the pressure, and either way, catalyst doesn't raise temperatures anyway. Increasing the pressure of the reactants, thus favoring the products, that's not something that a catalyst is going to do. So A is your only proper answer. As I mentioned in number 9, number 10 is essentially asking the same thing. Which reaction diagram shows the effect of using the appropriate catalyst in a chemical reaction? And what's happening here, letter A, of course, is the correct answer. And what's happening is, after the catalyst, the energy spike here needed to make that reaction go is much lower. That's what the dotted line is. Before the catalyst, it takes a bunch more energy, almost 3 times as much in this particular reaction, to get that thing heated up enough to get it started. Once it starts, the downhill slope is the reaction creating more energy, and that, of course, keeps that reaction going. That's it. I hope this has all helped you. Do your thing.